In this brief video, we'll take a look at how we could solve systems of equations using a different technique by formulating what we call matrix equations. And this is not a method that we altogether use very often just because Gaussian elimination works pretty well for most situations, although there are some circumstances where we deal with matrix equations. So here's what this would look like without getting into too much of the details. If I have a matrix equation of the form A times X equals A equals B, and I think I'll go ahead and write it this way. I think I'll use capital letters to denote matrices here. And if you think about this as you would an equation in algebra like 3x equals 12, then you could probably think about a couple of different ways to solve this. Well, there's the first approach, which would say to solve this equation, you would divide both sides by 3. And so if we divided both sides by 3, we'd get 1x equals 12 divided by 3, which is 4. And so we get x is equal to 4. Now, in working with matrices, we actually do not have division. So there is no matrix division. There's no such operation. And without getting into too much of the details here, there is multiplication. So in solving this equation here, we could actually solve it using multiplication. So how would we do that with multiplication if division was not allowed? Well, it's kind of a little tricky thing here, but if I took 1/3 of both sides, well, 1/3 is a multiplier. It is a fraction, but it's a multiplier as opposed to a divisor. So 1/3 of 3 is obviously 1, and 1/3 of 12 is equal to 4. So we've done the same thing, we've just done it using a different technique. So when I'm dealing with matrices, if I use the inverse multiplication as opposed to the division approach, then I could actually take the matrix A and multiply both sides by its inverse. Now, without getting into detail here, notice that we kept A inverse on the left of the right side. In other words, if we multiply by A inverse on the left of the left side, then we must also multiply by A inverse on the left of the right side. Now, I didn't actually mention anything about inverses here, but recall that 1/3 is actually 3 inverse. It's 3 to the -1. But when we're dealing with matrices, it isn't quite as simple to find the inverse matrix. So if A, for example, were, well, before I wrap that up, let me just go ahead and wrap this up. So these kind of, if you will, cancel out, and you're left with x is equal to A inverse times B. Okay. Now, if A is, for example, 1, 2, 3, 4, then it is not the case that A is 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's actually a little bit more complex than that, but we're not going to get into calculating the inverse in this video. We just have to know that we can do it. It can sometimes be done. So let me give you a couple of examples. Here we have this matrix equation, 2x plus 2y equals 10, 3x minus y equals 3. So what I'm going to do first is I'm going to take the coefficients of x and y in both of those equations and store them inside of this matrix. Okay, and then this second matrix here, this x matrix, will actually just contain lowercase x and lowercase y. It'll be the matrix that just contains our variables. And then over on the right-hand side, we'll have the constant stored in a separate matrix. And we're not getting into the details of matrix multiplication, but this is how it works. This is what we're referring to as our A matrix. That's our X matrix, and this is what we're calling our B matrix. Now, if we take and we write X, we now know that X can be solved for by taking A inverse and multiplying it by B. So X, recall, is the matrix that contains the two variables, and the inverse of A will be 2, 2, 3, negative 1, the inverse of that, multiplied by the B matrix, which is 10, 3. Okay, well, we don't necessarily need to know how to do that, but let's go ahead and do this computation using a calculator and see that whether we use Gaussian elimination or we use the matrix equation, this is solving a matrix equation. And the reason this is an equation is because it has an equal sign and there are matrices involved. So it's a matrix equation. Okay, so here I've just defined the A matrix, 2, 2, 3, negative 1, and now create a new matrix, but I think I want to call, actually I do want to call it B, so I could change its name if I wanted to, but I want to only have one column, and that's just going to contain the constants. So press enter, and what I want to do is I want to multiply A inverse, I guess I can't just do that, I need to do A inverse. You can see that it computes A inverse over here. It shows you what's inside of that matrix. And you can see that that is clearly not 1 over 2, 1 over 2, 1 over 3, 1 over negative 1. The way it's computed is a little bit more complex, but the purpose of this video is not to get into the mathematics of how this works and why it works. That's a longer discussion. And so what I want to do is I want to multiply that result by B, and I get the vector 2, 3. Now, that means that little x is equal to 2, little y is equal to 3. If, on the other hand, I had done the Gaussian elimination, I should get the same answer. Do 2 rows, 3 columns, 2, 2, 10, 3, negative 1, 3. And then I want to do the reduced row echelon form of C. You see that we get the same answer. We get x equals 2, y equals 3. So this leads to, this equals 2, 3, and if you trace across to see what the top row is, well, the top row says x is equal to 2, bottom row says y is equal to 3, and so we've just solved a matrix equation. Now, the reason I don't prefer this method in general is that there are some caveats. And the caveats are as follows. A must be a square matrix. A square matrix. And so square means that it has the same number of rows as it does columns. So usually we write that something like n by n. The key emphasis here is it has the same number of rows equals the number of, say the number of rows equals the number of columns. And so you can't use this method if you have, for example, if you have one equation and 4 variables, or 2 equations and 4 variables, where let's say you would end up with a matrix that looks like this, 2, 0, negative 1, 6, and maybe this top row says x plus y plus z equals 4, 2x plus 0y minus z equals 6. This is the A matrix, the coefficients. Notice those are the coefficients. That's a 2 by 3. So that does not satisfy the condition, and so you could not use this approach to solve. Now, here's the other thing. A inverse does not always exist. And that's another problem, right? Just because even if you have a square matrix, you still have to, you still might not be dealing with a matrix that is invertible, one that has an inverse. So those are 2 of the caveats, and I think we'll just go ahead and stop there. This does work for, if you have 3 equations and 3 variables, and you have A as a 3 by 3 matrix. Remember, that A matrix is just going to contain the coefficients. So if you have the same number of variables as you do equations, then you can start off using this method. You know that it might be possible to use this, but you still may not have a matrix that is invertible. And like I said, we're not going to get into those conditions here. But this is an alternative tool that just doesn't quite stand up to the other method that we're using if our task is strictly to solve equations.